Hello everyone, my name is Adamya Vashisth and I am presenting speed measurement using optocoupler. So now first of all, what is an optocoupler? So optocoupler is a device which utilizes LED and a photosensor to transfer optical signal through an optical interface. Now what does this actually mean? So from this diagram, as you can see, like this is the LED, this is the photosensor. LED is transferring light, which is our optical signal, and our photosensor is converting that optical signal back to electrical signal. So first electrical signal, then optical signal, and then back to electrical signal. And due to this setup, there's a special property which is called electrical isolation. Now, what is electrical isolation? So electrical isolation is if we vary the voltage in this first circuit or add some noise, then it doesn't affect the output of the second circuit. Now, this is called electrical isolation. Now, there are some advantages to use optocoupler over other devices. So, first is electrical isolation. Electrical isolation helps us reduce the noise. Now, second is high reliability, as there's no point of contact or physical contact in the device, so there's a less chance of mechanical failure and wear and tear. Now, there optocoupler is also very compact in design, and optocoupler is very versatile. It can be used from industrial control system to consumer electronics. Now, in this experiment, we are using a speed measurement trainer kit. This is the circuit diagram of our speed measurement trainer kit. Here's our power supply. Here's our 1 hertz clock for our reference. And here's our 7 segment display to see the readings. Now, this is our wave shaper. Here we connect the sensor. Here we connect the motor. The signal coming from sensor is get converted into wave through this wave shaper. And then here's a multiplier. This multiplier multiplies the frequency of this wave shaper output by 4. Now, this by 4 is not universal. It is due to a specific setup that we are using. And we are going to see why the times 4 in the next slide. Now, here, while we are doing RPM calculation, so what we do is, first of all, after the wave shaper, suppose the frequency came out to be F. Now, from this diagram, as we can see, like our disk is having 15 spikes. And due to these 15 spikes, our rotation per second is going to be f by 15 as f is the frequency of our wave shaper. Now to convert it to rotation per minute, we have to multiply our frequency with 60, not frequency, rotation per second with 60. Now f by 15 times 60 is equals to 4f. And here's the 4. So to directly convert our frequency to RPM, we just put a multiplier there, which is going to multiply our frequency by 4. Now this is our experimental procedure. So this is our speed measurement trainer kit. Here's our motor. Motor is having power supply from the speed measurement trainer kit. Here's our multimeter, which we are using for the voltage measurement. Here's our oscilloscope, which is giving us the output of the wave shaper. And to measure the readings of this experiment, we change the voltage. So by changing the voltage, the readings change. And to measure the readings, so first we are going to measure the RPM. And to measure the RPM, we are going to the multiplier after the multiplier part. And as you can see here, the RPM here is 349, which is almost similar to the frequency displayed here. And if we increase the power supply, so we are increasing the voltage. The voltage has been increased to 1.7. The RPM is almost 645. And here you can see it's almost close to the speed reading shown here. Now the next part is to measure the speed. To measure the speed, we go back to the wave shaper output. We switch to the speed. We reset the counter, and then we start the timer at the same time. And this is a 5-second timer. So here. Now, after this procedure, we have noted our wave shaper output frequency, our multiplier output frequency, our count, which is shown here, and the time that we have taken to perform the experiment. Now, how are we going to calculate the speed from this data? So first of all, we need to calculate the diameter. So diameter of our disk was 85 millimeter. Now we find out how much the one slot had traveled. So to compute the one slot travel, we do like pi times d divided by 15, as there are 15 slots. So it comes out to be 17.8 millimeter. Now to calculate speed from our counter, So we do total count by total time times 17.8 millimeters per second, which is the slot travel for one slot. And now to calculate a speed from the RPM that we have noted earlier, we just do RPM times pi d divided by 60. Now here's like data analysis and reading. So this is the reading that we have taken. So here you can see there's a motor voltage, here's the wave shaper output, multiplier output, display RPM, and here's the speed measurement reading. So here we have calculated the speed. Now this is our analysis of our data. So this is the display RPM and this is our multiplier frequency. It is split pretty linear in response and the readings are almost similar in both the cases. Now there are some precaution which needs to be followed. So please do not exceed the voltage above 3 volts and ensure that all the connections are correct and tight. And after this, we can also find other parameters of the motor. So one important aspect of a motor is its motor constant. And we can find that motor constant from the voltage and RPM that we have noted before. So there isn't a perfect formula, but there's a basic formula which provides the understanding between RPM and the voltage. So this basic formula provides a basic understanding. So this is RPM is proportional to V by K, where V is the applied voltage, K is the motor constant, IA is the armature current, and RA is the armature resistance. Now, by plotting the best fit line in the data that we have got, we can find the slope and intercept. And from there, the slope that we found out was 422.7362, and the motor constant is 0.0023. And now, if we know the RA of the motor, which is armature resistance, we can also find the IA of the motor. So with this experiment, we can just not only find the RPM and the speed of the motor, but also the inner parameters of the motor by which we can find the RPM without using any device. For example, using this formula, we can approximate like at this voltage, what should be the RPM. Thank you.